Hi everybody, welcome back to the Feynman Technique. It's been a while since I've done a video. This isn't going to be really Feynman integration per se. I just saw this on the channel Maths 505 and decided to give it a shot. We're just going to, we'll solve it using brute force Taylor series. I'll be using this identity right here. That's the, this infinite sum right here converges to pi over 4. It's not that difficult to prove. So go ahead and look that up. Actually, I think I've derived it on this channel before anyway. So anyway, let's get started. Well, let's just, since this is a double integral, let's just go ahead and let's just evaluate the inner integral. All right, so what is that? We'll call it f of t, because if we integrate this with respect to x, we're going to get a function of t. So we'll call it f of t. And it's just equal to the integral from 0 to 1 of the square root of x minus the square root of t over 1 minus xt times xt to the 1/4. Give me 1 second. This is a plus. Okay. All right, and this gets integrated with respect to x. All right, so now let's make the substitution that u is equal to tx. All right, so we're going to get, let's see, 0. This is x is equal to 0. That means u is also equal to 0. This is x is equal to 1. That means u is equal to t. Let's see, we're integrating with respect to x. So we need all things in terms of, let's see, we're going to u though. So we're going to want u and t. So what is x in terms of u? It's u over t. So this is the square root of u over t. And then square root of t just remains the same. This xt becomes a u. This xt becomes a u. All right, now let's rewrite this as two separate integrals. So our f of t is now equal to, well, let's see, let's bring out all the constants. So we're going to have, this is 1 over the square root of t, so that's t to the negative 1/2 times the integral from 0 to t of, let's see, we had a u to the 1/2 minus u to the 1/4, so that's just going to be u to the 1/4. Did I do that right? Yeah. U to the 1/2 minus u to the 1/4, that's right. Over 1 minus u hold on 1 second. Let's see. du is equal to t dx, or dx is equal to du over t. So now we still have this dx. Well, that's du over t. And we'll take care of that by adding or subtracting 1 from the exponent on the t that's already there. All right. But then we're going to have another integral. Now let's see. We're going to recover a, well, it's definitely going to be a t of some sort. So far we have a t to the 1/2, and then a t to the negative 1. So that's going to be to the negative 1/2. So we've taken care of this, and we've taken care of this, and that's all there is. All right. So now integral 0 to t of, well, let's see, we already took care of this. I already took care of that. So let's see, this is going to be u to the negative 1/4, right? Because all we'll have to consider is this part. All right, and then over 1 minus u All right. So that's what we have now. All right. Let's go further. We can rewrite this 1 over 1 minus u as the sum going from say n equals 0 to infinity of u to the n. And that's valid for u values going from 0 to 1, or actually negative 1 to 1. Let's see if we have that. Well, what's u equal to? U is equal to something that you get when you multiply t and x. Well, our t's and x's go from 0 to 1. So anytime you multiply anything that's in between 0 and 1 by something else that's in between 0 and 1, you're going to get something that's in between 0 and 1. So it would be valid to do that. Our u's are only going to be going from 0 to 1. So it's fine to rewrite that 1 over 1 minus u as the sum going from n equals 0 to infinity of u to the n in this case. So let's rewrite that. But actually, first, let's just say that our I is also equal to the integral from 0 to 1 of our f of t dt, right? It is, because we just defined f of t to be this thing in there. So that's true. All right. Okay, so now our f of t is going to be this, but rewritten a little bit. All right. So f of t is now equal to, let's see, t to the negative 3 halves, and then we'll have an integral going from 0 to t, and then we'll have the u to the 1/4, and then we'll have a sum as n equals 0 to infinity of u to the n du plus t to the negative 1/2 times the integral going from 0 to t of u to the negative 1/4 times the sum as n goes from 0 to infinity of u to the n du. Yeah, all right. So that's what that is. All right, now let's use properties of exponents to rewrite stuff a little bit. Let's see, we'll put this du over there, and we'll make this a u to the n minus 1/4. Likewise, over here, we'll make this a u to the n plus 1/4. And then we'll use Fubini's theorem, which is, you know, it's valid under certain conditions which are met in this case. So let's make this the integral going from 0 to t. And a sum where n equals 0 to infinity. All right. So there we go. We rewrote that a little bit. Now let's evaluate these integrals. Well, let's see. This part is going to become, let's see, what's this going to evaluate to? That's going to be, we'll do this one first. We'll go left to right. It's going to be u to the n plus 5/4 over n plus 5/4 evaluated from 0 to t. The 0 is not going to matter. So that we would be left with t to the n plus 5/4 over n plus 5/4. Yes, that's correct. T to the n plus 5/4. fourths over n plus 5 fourths. And we no longer need the du. And you'll notice that this is actually a t to the negative 6 fourths. So 5 minus 6 is minus 1, so we can just have this as n to the minus 1/4. All right, let's see what happens when we do similar things over here. Let's see, we're going to get u to the n plus 3/4 over n plus 3/4. Evaluated at t, so we're going to get t to the n plus 3/4 over n plus 3/4. And then of course this is a 2/4. 3 minus 2 is 1, n plus 1/4. Okay. So there is our f of t. So we know that our I is equal to the integral from 0 to 1 of our f of t dt. So if we go like this, 0 to 1 dt, integral 0 to 1 dt, and then integral 0 to 1 dt, we have I. All right. So let's go ahead and do that. Well, again, there's no problem using Fubini's theorem on this, so let's just go ahead and do that. So now this is the sum going from 0 to infinity of the integral. And again, the sum of the integral. All right. Well, what are we going to get if we evaluate these integrals? Well, let's see. This is constant. The denominator is constant, so we're going to get t to the n plus 3/4 over n plus 3/4. T to the n plus 3/4 over n plus 3/4. So t to the n plus 3/4 over n plus 3/4 from the 0 to 1. The 0 is going to cancel out. The 1 is just going to, so we're just going to have 1 over n plus 5/4 times n plus 3/4. There we go. That's it. 1 over n plus 3/4 n plus 5/4. All right, what are we going to get over here? Well, let's see. This is going to be an n plus 5/4 over n plus 5. Okay, exact same thing. In other words, we're going to get this. Now we don't need this dt anymore. And that's going to be equal to I. All right, let's see if we can somehow make use of this. All right. Well, first of all, let's multiply the top and the bottom of this thing right here by 16. So that will give us 32 over 4n plus 3. And then 4n plus 5. All right. Well, how are we going to get an alternating form out of that? Okay, we're going to have to use partial fractions. All right. I'm not going to bother showing it on the board. I'm just going to tell you this is what it is. This is going to be equal to the sum, or 16. We'll write it like this. This is going to be the sum as n goes from 0 to infinity of 16 over, 1 second. Minus the sum as n equals 0 to infinity of 16 over n plus 5. Yeah, and that's what it would evaluate to if you used partial fraction decomposition on that. I had already done it in my notes. I didn't feel like doing it on the board. But anyway, yeah, that's what you get. Okay, so that is this is I right here. All right, now how are we gonna somehow make use of this identity? Well, let's see what we get for our first terms. All right, for our first few terms. All right, well, we're gonna get 16, and then we're gonna have something else going on. All right, let's see, 0. Well, that's gonna give us a 1/3. Our n equals 0 term is 1/3. All right. I think I need to do something first. Yeah. You know what? Let's manipulate this a little bit. What I'm going to do is I'm going to add 1 to our index on n and then subtract it from our index on n in here. So that's just going to work out to be a 4n minus 1 in that case. And we'll do the same thing over here. That would be a 4n plus 1. All right, that might make it a little bit nicer to work with now. All right, so now what are we going to have? All right, let's see. Our n equals 1 term. We would have, let's see. We already took care of the 16, so we're going to have a 1 over 3. I don't know why that was so difficult for me. All right. And then what are we going to have? Well, we have this one too. So n equals 1 term. That's going to be a 1 over 5 minus 1 over 5. And then, let's see, our n equals 2 term plus 1 over 7 minus 1 over 9 plus 1 over 11, and so on, so on, so on. That's what you get if you add these two sums together. But what is that really? Well, that's 16 times the sum as n goes from 1 to infinity of, well, let's see. It's alternating, so we're going to have a -1, and our first term is positive, so it looks like that's going to have to be n plus 1. Yeah, yep. All right, and then over, let's see, that's going to be 2n plus 1. All right. Well, we almost have that. We can actually get that by adding a 0th term and then subtracting the 0th term. So now we need to subtract the 0th term of this thing. Well, it's actually going to be subtracting 16 times the 0th term of this thing. Let's see, 0 into here would give us a negative. All right, so we're going to have a negative. And 0 in here would give us a 1. So that becomes a plus 16. And now we can see that this is almost our correct form. Let's get rid of this plus 1 on our n and then bring it out as a negative. So let's see. Now this is exactly this. So we know that's pi over 4. So that's going to give us 16 minus 4 pi, right? That's going to be the final answer. 16 minus 4 pi. And yeah, that's it. That's the answer. I hope you guys enjoyed that.